In the last lesson, we examined how alcohols can be converted into alkyl halides by treatment with strong HX acid, where X is a halogen. The conversion of an alcohol into an alkyl halide is a useful process because alcohols actually tend to be more common functional groups. In the grand scheme of taking simple starting materials and making complex organic products out of them, you are much more likely to go in the direction of taking an alcohol and turning it into an alkyl halide rather than taking an alkyl halide and turning it into an alcohol. Alcohols are, first of all, more readily accessible from simple molecules like hydrocarbons, but secondly, alcohols are also the products of many important classes of organic reactions. So once you have an alcohol, you can then take it and convert it into an alkyl halide, which is a good leaving group. The question is, can we carry out a nucleophilic substitution reaction on an alcohol without using strong acid? So why would I ask such a question? The answer is that as you move forward in your organic chemistry course, you will realize that a large number of functional groups react with strong acid. Anytime your goal is to synthesize a complex molecule, you must always watch out for the undesired reaction of other functional groups that are present in your molecule. So for example, one reaction that you're going to learn about in the second semester of organic chemistry is the reaction of acetals with strong acid. And if you happen to have a molecule that has both an acetal and an alcohol, and you want to react the alcohol but not the acetal, you have to come up with a reagent that will discriminate between those two functional groups. So a lot of where modern organic chemistry research is actually coming up with reagents that exhibit some level of selectivity. So selectivity for one functional group over another is called chemoselectivity, and then as you get even more to a higher level, you start to think about reagents that are stereoselective. So we'll only give you one of two possible stereoisomers. But for the moment, we're looking for reagents that are chemoselective that will go after alcohols and turn them into alkyl halides under neutral conditions. So one such reagent is phosphorus tribromide. It's a reagent that converts alcohols into alkyl bromides, as you could expect given that there are bromides in the structure. Okay, so the overall reaction is as follows. If you take a garden variety alcohol, we'll use ethanol, reacted with PBr3, you will get out ethyl bromide. Same reaction that we carried out with HBr, but now we don't have the strong acid to worry about. So the detailed mechanism, step one, is activation of the alcohol to make it a good leaving group. Activation is a more general term that you use to take a functional group that's relatively unreactive and turn it into something that is more reactive. Protonation is a way of activating the OH, but by a similar mechanism, we can have the oxygen form a bond to the phosphorus and kick out Br as a leaving group to give something that has an oxygen with 3 bonds and a positive charge and also has a PBr2 on it. So it would be interesting to note the similarities of this reaction to the protonation with HBr reaction. You have a very similar structure in which the PBr2 fragment is functioning as a big fancy proton. Okay, so now once we've done this, we have generated bromide as a nucleophile, and it will come in and carry out the SN2 reaction on the primary carbon, and you now kick out PBr2OH as the leaving group. Thionyl chloride, SOCl2, is a reagent that converts alcohols to alkyl chlorides under neutral conditions. So similar overall reaction. We can start with an alcohol. We'll use ethanol again. In this case, instead of PBr3, we're using SOCl2, and the product is the alkyl chloride, ethyl chloride in this case. This mechanism is slightly more complicated than the mechanism for PBr3, but it would be instructive to look at this mechanism because this introduces a pattern that we're going to see both in the next lesson and then again in a later unit when we start talking about additions to carbonyl groups. So initially we want to activate the alcohol to make it a good leaving group, but in this case the activation process is 2 steps instead of just 1 step. The lone pair on the oxygen will attack the sulfur just like the lone pair on the oxygen attack the phosphorus in a PBr3 reaction. However, the sulfur now has the choice, if it's accepting more electrons from the oxygen, are you going to kick out one of the chlorines directly, or are you going to break the sulfur-oxygen pi bond? Because thionyl chloride, if you look at its complete structure, has an SO double bond. Well, if you think back to the early part of the course, you should realize that pi bonds are weaker than sigma bonds. So if we have the opportunity to break a pi bond rather than a sigma bond, we're going to do so, and that's precisely what happens. In forming the new oxygen-sulfur bond, we break the sulfur-oxygen pi bond. This gives us an intermediate in which sulfur is forming 4 single bonds, and there's a negative charge on the oxygen that is singly bonded to sulfur. Well, this is not a particularly happy place to be. It still wants to kick out chloride as the leaving group. So what's going to happen is those electrons on the O- are going to come down, reform the SO double bond, and kick out chloride as the leaving group. Why is this favorable? Because an SO- is still going to be a stronger base than Cl- is. So while, again, this is not an acid-base reaction strictly, anytime you have a reaction that can generate a weaker base, that's going to frequently be a major driving force behind that reaction. So then step 2 is the SN2 reaction with chloride as the nucleophile. So the chloride that got kicked off comes in, attacks the primary carbon, and then you've generated the alkyl chloride, and in this case, SOClOH is kicked off as a leaving group, and it turns out that that further breaks down to give sulfur dioxide, SO2, and HCl, hydrochloric acid. Those are both gases. They can both eliminate, evaporate, bubble out of the solution, and that will remove them from contention as any possible way to get further involved in the mechanism of this reaction. Okay, so we've seen PBr3 as a reagent that converts alcohols into alkyl bromides, and SOCl2 as a reagent that converts alcohols into alkyl chloride.